Hello, this is Mr. Ambrose, and I'm going to go over one of the problems from the gift you received on Monday, specifically question number 10. So, moving along to that problem, we see in this question it says monthly mortgage payments can be found using the formula below. So this is one of the questions where you're given the particular formula, and then below that you're told specifically what each variable represents within that formula. So N represents the monthly payment, P represents the amount borrowed, R equals the annual interest rate, and N equals the number of monthly payments. Then we're told that the Banks family would like to borrow $120,000 to purchase a home. They qualified for an annual interest rate of 4.8%. Algebraically determine the fewest number of whole years the Banks family would need to include in the mortgage agreement in order to have a monthly payment of no more than $720. So, as you had to do in the last unit, with these types of formulas, we should perhaps try to identify exactly what each of the variables are that we have, and then put them into our formula to set up a formula to allow us to solve for what they're asking us for. So we'll start off with the variable m. And in this particular problem, again, m represents the monthly payment, and we're told that there's a monthly payment of $720. So we'll write that in. Then the value p, the variable p, represents the amount borrowed, and we're told the Banks family would like to borrow $120,000. So p is going to equal $120,000. R is our annual interest rate, which we're told is 4.8%. So as a decimal, and that's how we have to input it into our equation, that would be written as 0.048. And then N is the number of monthly payments, and technically that's what we're being asked to find. They asked us to find the number of whole years the banks would need it to include in the agreement, and the number of monthly payments corresponds to the time value that we're being asked to solve for. So N is going to be the variable in our equation that we're going to have to try to solve for. So with that, we'll now go to our equation and start plugging in these particular values. So we have that M, which again is 720. That's going to equal P, which is 120,000, times R over 12. R is the 0.048. Again, that's over 12. And then we have to multiply that also by 1 plus R again, which is 0.048. Over 12, and then that parenthesis there is raised to the nth power, which we don't know what that is, and then that's all over 1 plus R again, that's 0.048 over 12, and that's raised to the nth power. And then we have to subtract 1 from that. Right. So that's our equation. We have it all set up. And now we're going to have to try to solve for the n in our equation, which unfortunately there's an n here and an n there. We're going to have to try to solve for what that value then is. All right. So with that, algebraically, we're going to have to try to use our algebra that we know. And so one of the things we can start doing is there's certain computations we can start actually performing. For example, what's inside the parentheses, this 1 plus 0.048 over 12, we can actually calculate what that's equal to. And that should end up being just 1.0 0.004, and that would be raised to the nth power. This 120,000 times the 0.048 over 12. There's nothing else happening except for this multiplication, this division, so we can actually calculate what that all will equal. And when we multiply that out, we should get a value of 480. And then in the denominator, again, we have this 1 plus 0.048 over 12. We can rewrite that as 1.004 raised to the nth power, and then we have minus 1. So we've simplified things down, and the original equation, I'm sure, is somewhat intimidating, but now we have something a little bit simpler. But we still have to try to solve for the n variable, which is located in the exponent. So if you recall, with these types of problems, when we solve them algebraically, we have to get the exponent, the base, and the exponent all by itself before we can try and take the natural log of both sides. And because we have this fraction over here, what we'll do is we'll multiply both sides by this 1.004 to the n minus 1, so that we can kind of get rid of this fraction on the right-hand side. So doing that, we'll have that 720 will be multiplied by 1.004 to the nth power minus 1. And then on the right-hand side, we'll just be left with the numerator, 480 times 1.004 to the nth power. You'll notice that over here on the left side, I've left the 720 out in parentheses because we have to really, if we properly multiply that left side by the denominator over here, we're going to have to distribute in the 720 to both of these terms. So doing that next, I would have 720 times 1.004 to the nth power. You'll notice that I'm not multiplying the 720 to the 1.004 because by order of operations, I have to take 1.004 and raise that to the nth power first before we can multiply by 720. So I just leave it as is. And then 720 times negative 1 is just minus 720. This is still going to equal the right-hand side of 480 times 1.004 to the nth power. Now, you'll notice that we have here this exponential expression, 1.004 to the nth power, and this exponential expression as well, 1.004 to the nth power. These two terms are like terms because they have the same base and exponent. So to help with getting them by themselves, we'll subtract both sides by 720 times 1.004 to the nth power. And when we do this, on the left-hand side, what we'll just have there will be negative 720. And on the right-hand side, these are like terms. So we can take the 480 and subtract 720 from that to get minus 240 times the 1.004 to the nth power. And now, this should hopefully look somewhat more like the problems we've been dealing with. To get this exponential expression by itself, we would just now have to divide both sides by negative 240. That would leave us with 3 on the left-hand side and 1.004 to the nth power on the right-hand side. And now that we have the exponential expression all by itself, we can take the natural log of both sides And by the power rule of logs, on that right-hand side, we can bring down that exponent of n, the power of n, and then the last step to solve for n is we would need to divide both sides by the natural log of 1.004. And if we do that, we should get an n value of 275.2. And we've now solved for n. But the tricky thing is that in the problem, n represents the number of monthly payments, and they wanted to know what are the number of years. Right? We have to solve the number of whole years that will be required to get for the banks to pay off their loan. So now that we know what n is, which is the number of months, we would have to take that 275.2. Again, remember this is months, and to figure out the number of years, we would have to divide that by 12. And when we divide that by 12, we get 22.9, which rounded to the nearest whole year would give us 23 years. Right? So that's how we solve this type of a problem. Again, it's a bit daunting, and there's a lot of steps involved. Obviously, you want to set up your equation carefully first, and then use the algebra that you know to carefully navigate your way through this particular question. So hopefully this helps, and the next time that we meet in class, we'll go over the review sheet and any other questions you might have. Take care.